The story of the Grand Slam bomb is a compelling tale of engineering ingenuity pitted against seemingly impossible fortification. The German construction program during World War II created a monumental defensive line known as the Atlantic Wall. This defensive barrier stretched thousands of miles from Norway down to the Spanish border. Within this massive structure, German engineers poured millions of tons of concrete into building structures intended to withstand any conventional aerial assault. These were not simple pillboxes, but colossal bunkers, submarine pens, and V-weapon storage sites designed to be absolutely impenetrable. The U-boat pens, in particular, represented a significant threat that demanded an immediate and decisive countermeasure. These gargantuan shelters boasted roofs often 5, 6, or even 7 meters thick, a depth of reinforced concrete specifically calculated to defeat the heaviest bombs available to the Allies. The men who designed these bunkers were supremely confident in their calculations and their materials. They believed they had achieved a permanent, technological superiority over the Allied air forces. The German strategy hinged on the idea that their vital assets, especially the U-boats that terrorized Atlantic shipping, could operate from bases completely immune to attack. This confidence was rooted in the proven failure of earlier Allied bombing raids, which had peppered the steel and concrete shelters with little effect. Conventional high-explosive bombs simply detonated on the surface, causing superficial damage that could be quickly repaired by the dedicated German labor forces. The concrete was not merely poured. It was often vibrated and reinforced with staggering quantities of steel rebar, creating a composite defense of immense strength. To the Allied strategists, these shelters became a symbol of German arrogance and a crippling operational problem that required a radical solution. The need to neutralize these bunkers was paramount, as the U-boats they protected continued to choke the vital supply lines keeping Britain in the war. A new weapon, a completely revolutionary approach to aerial bombardment, was required to turn the tide against these concrete monsters. The battle was no longer just in the air or on the sea, but it had become a contest between materials science, structural integrity, and destructive force. The German engineers had thrown down a formidable gauntlet that the Allies had no choice but to pick up, demanding an answer that was as massive as the fortifications themselves. The man who would answer this technological challenge was a figure already famous for his unconventional thinking, Sir Barnes Wallis. Wallis was a British engineer and inventor whose name was already legend in certain circles for his work on airships and the revolutionary geodetic airframe design of the Wellington bomber. His mind, however, was perpetually focused on the problem of how to achieve true, decisive destruction from the air. He was not interested in area bombing, which he considered inefficient and immoral, but in surgical strikes that eliminated vital targets with extreme precision. Wallis understood that simply making a bomb bigger would not solve the problem of thick concrete. A fundamentally different principle of attack was needed. He theorized that a bomb could be designed not merely to explode on impact, but to create a seismic shockwave, acting as an artificial earthquake. This concept required the bomb to strike the ground at supersonic speed, burying itself deep into the earth before its fuse triggered the main detonation. The idea was to attack the target not directly, but from underneath, causing the very foundations and surrounding soil to fail, shattering the structure from below. Wallis's initial designs for such a weapon were met with skepticism and resistance from military officials who favored more conventional bombing doctrine. His vision was considered too fantastical, too radical, and his required engineering tolerances seemed impossible to achieve in wartime manufacturing. Despite the institutional inertia, Wallace persistently pushed his theory, drawing from his deep understanding of structural dynamics and aerodynamics. His earlier triumph with the Dambusters raid in 1943, where his bouncing bombs successfully breached major German dams, had given him the necessary credibility to pursue his next, even more ambitious projects. The bouncing bomb proved that Wallace was a genius capable of turning theoretical physics into devastating practical reality. This success provided the political and financial capital to begin development on his next generation of specialized weapons. Wallace believed that the German bunkers were only vulnerable if the principle of attack fundamentally changed from percussion to earth displacement. He was driven by a deep desire to reduce the loss of Allied aircrew by making every single sortie count toward the elimination of a critical strategic objective. The engineering task was colossal, requiring a bomb casing strong enough to survive a high-velocity impact with the ground without shattering. It also demanded a highly specialized aerodynamic shape to ensure supersonic terminal velocity and a vertical trajectory upon hitting the target area. Wallace's initial answer to the fortress problem was the development of the Tallboy bomb, the first true earthquake weapon. The Tallboy was an impressive weapon, weighing 12,000 pounds, a significant increase in size over standard Allied heavy bombs. Its distinctive feature was its streamlined, aerodynamically refined shape, complete with spiral fins that imparted a high rate of spin during its descent. This spin ensured the bomb would remain stable at high speed and would drill itself deep into the earth upon impact. The casing of the Tallboy was forged from high-strength steel, designed to withstand the tremendous shock of hitting the ground at close to the speed of sound. It was carried by specially adapted Avro Lancaster bombers, which had to be stripped of excess weight and fitted with modified bomb bays to accommodate the sheer size of the weapon. The precision required for deployment was immense, with bombing crews needing to drop the bomb from an altitude of around 18,000 feet to allow it to build sufficient velocity. Tallboy quickly proved its revolutionary potential against heavily defended targets that had previously been considered untouchable. It was deployed against fortified railway tunnels, bridges, and hardened military installations across Europe with devastating success. The bomb's performance was exactly as Wallace had predicted, as it bypassed external defenses and caused catastrophic structural damage from below. In one notable success, a Tallboy struck a hardened tunnel in France, collapsing the structure and sealing off a vital route for German troop movements. It successfully destroyed viaducts that had withstood hundreds of conventional bombing raids, proving the viability of the Earth penetration concept. The Allied forces now had a weapon that could not only destroy, but also utterly incapacitate targets by destroying the very ground they stood upon. However, even the Tallboy, for all its power, found its limitations when faced with the sheer, unprecedented scale of the largest German superstructures. Some of the U-boat pens and massive concrete strongholds had concrete roofs that were simply too thick, too deep, and too resilient even for the 12,000-pound blast. The Tallboy could shake the foundations, but it could not always deliver the decisive, roof-breaching knockout blow that was required for absolute target elimination. The German response was to continue building even larger, thicker bunkers, convinced that they could outbuild the Allied bomb developers. This escalation forced Wallace to look beyond the Tallboy and conceive of a weapon that would be, quite literally, the ultimate expression of the earthquake bomb principle. The U-boat war was a relentless, grinding campaign that pushed Britain to the very brink of starvation and economic collapse. The German submarine fleet, operating from secure bases along the French and Norwegian coasts, sank millions of tons of Allied shipping. The key to the U-boat's survival was not just its stealth in the Atlantic, but the construction of impregnable bunkers in port. These vast concrete cathedrals were built primarily to provide a safe haven from the incessant Allied air raids. The shelters were designed so that an entire U-boat crew could berth, repair, and rearm their submarine without any fear of the bombs raining down outside. The sheer scale of the construction was staggering, often employing forced labor and consuming an enormous percentage of Germany's cement and steel production. Sites like the U-boat pens at Lorient, Brest, and La Rochelle became legends of military engineering. Their roofs, measured in meters of reinforced concrete, stood as a defiant symbol of German technical mastery. Allied air commanders grew increasingly frustrated as hundreds of sorties were expended against these facilities with almost no strategic result. The bombs would explode with a thunderous roar, but the U-boats inside would remain untouched, ready to slip out on their next patrol. This immunity provided a psychological boost to the German Navy, convincing their crews that the Allies could never truly reach them at home. It also meant that the Allied bombing raids were a tremendous drain on resources, fuel, and, most tragically, the lives of aircrew. The persistence of the U-boat threat was one of the most significant factors prolonging the war in the Atlantic. These concrete monstrosities also housed workshops, storage facilities, and crew quarters, making them self-contained, critical logistical hubs. Their existence meant that the U-boat fleet could sustain a high tempo of operations without ever having to worry about maintenance vulnerability. The thickness of the concrete was determined by precise German ballistic testing, calculated to absorb the energy of any known Allied bomb. The German engineers' calculation was correct for conventional ordnance, and even the early versions of the Tallboy bomb. The bunkers were a living monument to the principle of defense through passive resistance, daring the Allies to develop a weapon that could truly pierce their shell. This defiance provided the final, undeniable proof that the Allies needed a weapon of a completely different magnitude to achieve strategic success. The U-boat pens, more than any other target, were the specific and ultimate reason for the creation of the Grand Slam. The limitations of the Tallboy bomb, particularly against the most heavily protected targets, immediately spurred the development of its successor, Barnes Wallis, driven by the continued reports of unyielding German bunkers, started work on a colossal weapon that would be twice the size of his previous design. The new bomb was codenamed Grand Slam, an apt title for a weapon intended to deliver the ultimate knockout blow to the enemy's most fortified assets. The sheer mass of the Grand Slam was astonishing, weighing in at a full 22,000 pounds, or almost 11 tons. The manufacturing challenge was formidable, requiring specialized facilities to cast and machine the enormous, high-strength steel casing. This casing had to be utterly perfect, as any structural flaw could lead to a catastrophic failure upon impact at high velocity. The British government, having witnessed the success of the Tallboy, prioritized the production of the Grand Slam, recognizing its potential to break the strategic deadlock. The design team at Vickers, led by Wallis, refined the aerodynamics of the bomb, ensuring it had the same stabilizing spin as its smaller predecessor. This rotational stability was crucial for maintaining a vertical trajectory as it hit the Earth, maximizing its ability to penetrate before detonation. The logistics of handling and transporting such a massive piece of ordnance also presented unprecedented difficulties for the Royal Air Force. Airfields had to be specially modified, and specialized trolleys and hoisting equipment were required simply to move the bomb from the storage magazines to the aircraft. The airframe of the Avro Lancaster, the workhorse of Bomber Command, also needed further, more radical modification to carry the 11-ton payload. The bomb bay doors had to be removed entirely, and the internal structure of the fuselage needed significant strengthening to bear the concentrated weight. Only a select few Lancasters were chosen for this transformation, becoming known as BI Special Types, representing the pinnacle of wartime aircraft modification. The crews assigned to fly these leviathans of the air were the elite of the elite, requiring exceptional flying skill to handle the heavily burdened aircraft. Their mission was not area bombing but pinpoint delivery, demanding the highest degree of navigational and bombing accuracy. The race was on to field the Grand Slam before the end of the war, as every month that passed meant more U-boats and more V-weapons being protected by the thickest concrete in the world. The development of the Grand Slam was a massive commitment of engineering, industrial, and human resources, all focused on creating a decisive, war-winning weapon. The Grand Slam was far more than just a scaled-up version of the Tallboy. It represented a new level of ballistic engineering precision. The enormous bomb was approximately 25 feet long, dominating the fuselage of the aircraft that carried it. Its weight, a staggering 22,000 pounds, was a deliberate design choice intended to maximize kinetic energy upon impact. The massive steel casing was meticulously shaped to ensure minimal air resistance and maximum velocity on its freefall descent. Barnes Wallis calculated that the bomb would strike the Earth at speeds approaching 1,000 feet per second, an astonishing terminal velocity for a weapon of this size. To achieve its earthquake effect, the bomb was filled with over 9,500 pounds of high-grade Torpex explosive. Torpex, an explosive far more powerful than conventional TNT, was chosen to generate the most violent shockwave possible underground. The fuse of the Grand Slam was deliberately delayed, calculated to allow the entire mass of the bomb to bury itself deep beneath the target's foundation. This delayed detonation was the critical mechanism for the earthquake effect, shattering foundations and causing structural collapse. The thick steel casing was a crucial innovation, designed to ensure the bomb survived the initial impact and burrowing process intact. Without this incredibly strong casing, the bomb would have simply broken apart or detonated prematurely on the surface, rendering it useless. The spiral-grooved fins on the tail section were another key design feature, ensuring a high rotational spin for aerodynamic stability. This spin prevented the massive bomb from tumbling during its descent, guaranteeing a precise, vertical strike on the target zone. The precision required in the manufacturing process meant that each Grand Slam was essentially a bespoke piece of ordnance. Casting the giant steel shells without internal flaws required innovative metallurgy and extremely slow, controlled cooling processes. The Grand Slam was, in essence, a guided missile of gravity, its trajectory and destructive power governed entirely by aerodynamic perfection and sheer mass. Its existence immediately altered the defensive calculus of German engineers, who now had to contend with a weapon that rendered their thickest concrete roofs obsolete. The design was a bold statement that no structure on Earth, no matter how reinforced, could stand up to the combined forces of kinetic energy and subsurface blast. The sheer weight and size of the Grand Slam bomb necessitated a radical transformation of the venerable Avro Lancaster bomber. The standard Lancaster, even the heaviest variants, was not designed to lift and safely carry an 11-ton payload. The modifications were so extensive that the chosen aircraft were specifically designated as Lancaster BI, special, for this unique mission. The most visible change was the complete removal of the bomb bay doors, exposing the massive bomb to the slipstream for the duration of the flight. The structural elements of the fuselage around the bomb bay had to be significantly reinforced with additional bracing and high-strength alloy. The mid-upper turret and the main armor plating were often removed to reduce the overall weight of the aircraft. This weight reduction was critical for maintaining a viable fuel load and a necessary margin of safety for takeoff and climb. The flight characteristics of the modified Lancasters were drastically altered, making them heavy, sluggish, and far more challenging to fly. Pilots described the takeoff run with a Grand Slam as a terrifying, slow, and lumbering affair, pushing the Rolls-Royce Merlin engines to their absolute limit. They required maximum power and an exceptionally long runway to reach the necessary liftoff speed before the end of the tarmac. The crew complement for Grand Slam missions was also specialized, relying on the most experienced and calmest airmen in Bomber Command. The navigators and bomb aimers were required to perform under extreme pressure, knowing the value of the single weapon they carried. Every mission became a high-stakes, one-shot attempt to destroy a target that could not be missed. The specialized squadrons tasked with these missions, such as Number 617 Squadron, the famous Dambusters, were chosen for their proven precision. Their training involved relentless practice in high altitude, precision bombing techniques to ensure the Grand Slam landed exactly on target. The delivery of the Grand Slam required a perfect combination of precision navigation, stable flight, and accurate bomb aiming from 18,000 feet. The entire success of the mission hinged on the ability of the pilot to maintain a steady course and the bomb aimer to release the weapon at the exact, calculated moment. These modified Lancasters were the unsung heroes of the Grand Slam story, acting as the necessary, powerful launch platform for the decisive weapon. They were a testament to the engineering and operational flexibility of the Allied air forces in adapting existing technology to meet new strategic needs. One of the most colossal and defiant of the German fortifications was the U-boat construction bunker known as Valentin. Located near the village of Farge on the River Weser, north of Bremen, it was intended to be a factory for assembling the revolutionary-type XXI U-boats. The German plan was to churn out fully assembled, technologically advanced submarines that could change the entire balance of the war at sea. Bunker Valentin was a structure of truly staggering proportions, measuring 426 meters long and up to 97 meters wide. Its roof was initially planned to be 7 meters thick, a measure that German engineers believed made it impervious to any Allied aerial bombardment. The construction of Valentin was a massive undertaking, utilizing thousands of forced laborers under brutal and inhumane conditions. It represented a final, desperate attempt by the Nazi regime to secure their naval superiority through industrial fortification. To the Allies, This bunker was not just a military target, but a symbol of the enemy's unyielding determination to continue the war. The intelligence gathered on Valentin confirmed its status as a critical objective that, if operational, would pose an existential threat. The enormous complex was still under construction in early 1945, but its imminent completion made its destruction a matter of extreme urgency. Conventional bombing had been attempted against the surrounding area but proved completely ineffective against the thick roof sections already completed. The sheer mass and thickness of the concrete defeated even the smaller Tallboy bombs in initial testing and limited strikes. This failure directly paved the way for the deployment of the Grand Slam, the only weapon capable of a truly decisive strike. The mission against Valentin was not just about destroying a structure. It was about destroying a concept, the idea of an unsinkable, unassailable industrial fortress. The psychological impact of destroying a structure of this scale would be enormous on both the German command and the Allied forces. The date was set for a surgical strike by the specially trained No. 617 Squadron, armed with the new 11-ton behemoths. The successful destruction of Valentin would save countless Allied lives and shorten the war in the Atlantic theater. The attack would be a direct challenge to the German engineers' proud claim of having built an impenetrable structure. The operational use of the Grand Slam demanded a level of accuracy unprecedented in the history of strategic bombing. The sheer cost and rarity of the weapon meant that misses were simply unacceptable, especially against primary, hardened targets. The crews of No. 617 Squadron, already veterans of specialized missions, were trained to treat the Grand Slam as a non-releasable weapon until all conditions were perfectly met. The high-altitude release was necessary to achieve the maximum kinetic energy for the Earth penetration effect. However, bombing from 18,000 feet introduced significant variables due to wind drift, air density, and the need for a precise visual aiming point. The squadron relied on the Advanced Stabilized Bomb Sight, a device designed to compensate for the aircraft's movement and environmental factors. This bomb sight provided the crucial, final moment of aiming accuracy required to hit a relatively small target from a great height. The target was often obscured by the natural camouflage and the inevitable smoke and flak from the surrounding German defenses. The lead bomb aimer was tasked with the nerve-wracking job of identifying the precise aiming point and giving the command for the single, final release. This moment was the culmination of weeks of planning, specialized aircraft modification, and intense crew training. The modified Lancasters, struggling under the massive load, had to maintain a perfectly steady, straight, and level run-up to the target. Any slight deviation in speed or altitude could throw the 10-ton weapon hundreds of yards off course. The Grand Slam's trajectory was also subject to small, unpredictable atmospheric variations as it plummeted toward the Earth. The success of the mission depended on the perfect execution of all these complex elements in the face of enemy anti-aircraft fire. When the Grand Slam was finally released, the massive reduction in weight caused the Lancaster to instantly surge upward, a phenomenon known as lightning. This sudden change in flight attitude required immediate, corrective action from the pilot to maintain control of the now much lighter aircraft. The entire sequence, from the final approach to the moment of release, was a testament to the skill and bravery of the Allied air crews. The aim was not simply to hit the bunker, but to hit the specific spot that the intelligence had determined to be the most vulnerable area. The day the Grand Slam arrived over its intended target marked a definitive end to the era of the impenetrable concrete fortress. On March 27, 1945, two Grand Slams were dropped on the U-boat construction Bunker Valentin by the RAF's No. 617 Squadron. The first bomb struck a nearby embankment, a near miss that caused a significant local earthquake, but the second bomb found its mark. The enormous weapon plunged through the partially completed, yet incredibly thick, concrete roof of the bunker. The bomb penetrated the 5-meter thick reinforced concrete roof near the northwest corner of the structure. It was the first time that any aerial weapon had successfully breached such a colossal defense mechanism. The force of the impact alone was enough to severely weaken the surrounding structure and send massive shock waves through the entire complex. The delayed fuse then triggered the detonation of the 9,500 pounds of Torpex deep within the confines of the massive concrete shell. The resulting explosion was catastrophic, far exceeding the damage that any previous bomb could have inflicted. A colossal section of the roof, estimated to be several thousand tons of concrete and rebar, was lifted and disintegrated by the force. The roof violently collapsed into the construction hall below, causing immense damage and killing many of the forced laborers inside. The resulting hole in the roof was approximately 8 meters across, a gaping wound that rendered the entire section of the bunker unusable. The seismic shock wave traveled through the foundation, causing significant cracks in the walls and structural failure in key support columns. The Grand Slam's success proved Wallis's theory correct, demonstrating that a target could be destroyed by attacking its foundations and substructure. The destruction was not superficial, but a total structural failure that immediately halted all construction and rendered the multi-million-ton facility permanently obsolete. This single, precise strike with one bomb achieved what hundreds of conventional bombs had failed to do over several years of attempts. The German engineers' confidence in their concrete was utterly shattered by the arrival of the Grand Slam. The destruction inflicted by the Grand Slam was a massive strategic victory that went far beyond the physical damage to the concrete. The successful breaching of the Valentin bunker's roof sent an immediate and unambiguous signal to the German High Command. No longer could they rely on their monumental fortifications to protect their most vital military and industrial assets. The psychological impact of this single bomb was devastating, undermining years of effort and immense expenditure on concrete construction. Following the success at Valentin, the Grand Slam was immediately deployed against other critical, hardened targets across the German-occupied territories. It was used to eliminate heavily reinforced U-boat assembly facilities, V-weapon storage tunnels, and key bridges and viaducts deemed impervious to all other bombs. Each successful strike shortened the war by removing a critical bottleneck or eliminating a major threat to Allied forces. The Grand Slam was instrumental in destroying a number of hardened railway bridges that were essential for the movement of German reinforcements to the front lines. By causing subsurface damage, the bomb often took targets completely out of commission for months, a much longer and more effective result than superficial damage. The German military was forced to shift resources away from the front to assess, and, in vain, attempt to repair the damage caused by the giant bombs. The ability of the Allies to now strike any target, no matter how protected, allowed for a complete reassessment of their strategic bombing campaign. The era of absolute immunity for German fortifications had definitively ended with the deployment of the 11-ton bomb. The mere threat of the Grand Slam forced the Germans to abandon certain construction projects and disperse their critical assets. It was the ultimate vindication of Barnes Wallis's persistent vision and his belief in specialized, decisive weaponry over mass bombing. The bomb's strategic importance cannot be overstated, as it cleared the path for the final ground offensives of the war. The Grand Slam proved that there was no such thing as an impenetrable structure if the engineering genius was matched to the destructive force. Its operational history is a clear demonstration of how a single technological innovation can break a strategic deadlock in a major conflict. The legacy of the Grand Slam bomb extends far beyond the final days of the Second World War. The weapon fundamentally redefined the limits of aerial bombardment and forced a permanent change in military engineering and fortification design globally. No nation could ever again design and construct a fixed defensive structure with the absolute confidence that German engineers once held. The concept of the earthquake bomb, successfully executed with both Tallboy and Grand Slam, became a core doctrine in post-war military strategy. The principles of using kinetic energy and subsurface detonation to induce structural failure remain relevant in modern military planning. The ruins of the mighty German bunkers, such as the colossal, shattered remnants of Valentin, stand today as silent, powerful monuments to the bomb's success. They are physical proof that there is always an engineering countermeasure to even the most elaborate defensive structure. The design work of Sir Barnes Wallis on the Grand Slam cemented his reputation as one of the most innovative and impactful engineers of the 20th century. His commitment to precision, efficiency, and decisive action changed the course of the war and the future of military technology. The specialized Lancasters that carried the Grand Slam also hold a unique place in aviation history, representing the ultimate adaptation of an airframe. Their missions underscore the incredible risks and dedication of the aircrews who delivered these single, war-altering blows. The Grand Slam was, in many ways, the ultimate expression of the technological race that defined the Allied war effort. It was the final answer to the German U-boat menace and a decisive blow against the formidable strength of the Atlantic Wall. The story of the Grand Slam is a classic lesson in the history of warfare. For every defense, there will always be a new offense. The single 10-ton weapon ended the era of the concrete behemoths, leaving behind a legacy of destruction that was strategically critical for the Allied victory. The weapon's name itself, Grand Slam, perfectly encapsulated its purpose as the ultimate, game-winning strike against the enemy's seemingly unassailable defenses. The weapon's success remains a powerful reminder of how innovation can overcome a seemingly insurmountable technological challenge.